FCC vacancy.
Hello. I'm going to go on from where we talked yesterday about hyperfine structure in the radio frequency spectrum from active cold fusion systems. And what I'll show you today is two results. One, where we see super hyperfine structure. These are sidebands that have been discovered within the hyperfine structure only when we have an active cold fusion system. And I will show you the results from both palladium with zirconium oxide and also with nickel. So I'm going to just review a few percent of the slides from last time just to redo it. Cold fusion systems have excess heat, they know over helium, low-level emissions. We've shown anti-Stokes spectra, and now we see deuterium line emission as well. And here is one of them that I showed you, and what I will show you shortly is by increasing the applied electric potential, these separate into sidebands. And the sidebands may be revealing structure. I showed you, in fact, that here we're seeing frequency here, 327.3 megahertz, 327.385 megahertz. Here is the maser. We've taken the nanor component. It's a two-terminal dry preloaded device with an electric current going through it on the order of microamperes. And what happens is as soon as we turn it on at a few volts, we get a slight drift. Finally, we get equilibrium. These are galactic lines. Time is actually going this way. This is called a waterfall. This is instantaneous in one section, one point of time. So as I showed you yesterday, what we see is that active electrically driven components give out the deuterium line in both the dry preloaded and the nickel ordinary water system. What we also showed was it has a positive Zeeman effect that is applying a magnetic field. We get splitting. And what I'm going to show you today is an analysis of the non-Zeeman splitting. These do not have a magnetic field applied, but they're a result of where the activated deuterium is in the lattice. They have a very high Q. One of the most amazing things as an electrical engineer, we're always told how big the electromagnetic spectrum is. And here, within 30 kilohertz, you'll be able to see the entire structure of the lattice. The origin of the hyperfine line is that we have an interaction between the deuteron nucleus and the deuteron electron. This is a free radical somewhere within our system. Thank you. And what happens is in the microwave region, the upper state is stable, and as a result of stimulated emission within the Fabry-Perot cavity, we then get a de-excitation. And people have used this to look into space. One joke is why are we always looking for intelligence up there instead of down here? But let that go. One of the things you have to do, and I hope some of you try this, is you have to either use the Earth to shield the interfering electromagnetic spectrum from the Milky Way, which you can see here, or what you really need to do is a dual Faraday cage. So these are the materials. I'm going to show you the super hyperfine lines of the mother of all cathodes. It's a half a mile of nickel wire. This is unfilled. We fill it with 3 liters of water. We've shown that the deuterium falls as this runs over months. And the fact that, as I showed you at ICCF21, there are 2 states to electrically driven cold fusion systems. One gives excess heat, and it's really easy to swing into the mode where there's no excess heat. So here, for example, with the mother of all cathodes, this is an ohmic control. The input power here, this is the output heat. Yet with the cold fusion system, even with lower power going in, we get massive heat production until we switch to the inactive mode, and then we get hydrogen evolution. And then I will also show you the results of the dry preloaded, and those we also get excess heat from. Here's the ohmic control. Here is the 2-terminal component, much less input power, much more heat out, and we always correlate it by doing the integral to show that there's excess energy. And one last point, when you use the dry preloaded materials, if you go beyond the voltage that it can handle, you'll suddenly get a drop of the voltage from 800 volts down to 20 volts, and the current will go from microamperes to milliamperes, and you will get no excess heat, as you see here. This is ohmic control. Here we're getting nice excess heat, and I'm taking the system until it goes to avalanche, and then it matches with the ohmic control. And also, when you have an active system, there's the anti-Stokes, but now's not the time to talk about it. So the methods, just to review, is we put the active cold fusion device here. We have an antenna. This is the Fabry-Perot box. You can't see the Faraday cage around it. And then we take it to an amplifier, put it into a digital receiver, and into a computed system. Yesterday, I discussed some things about SWR matching, how we handle the transmission line loss, which is major, and the need for the low noise amplifier. The Fabry-Perot cavity, here we see the two-terminal component. I put it in a white envelope because if any of the material came out, I would see it from outside. That's what the purpose of the white envelope is for. And I told you that you have to use double Faraday cages because here we see the galactic interference, and yet if we ground the box correctly right into the ground with a copper rod, we get a nice empty space here, and we can really do some research. We use a normal mode helix antenna. We can skip over this. We did it yesterday. When you do this with radio frequency analysis, it's very similar to calorimetry. And the terms are somewhat similar, with the unit being the Jansky. If you want to talk about it later, we can. The most important thing about radio frequency analysis, unlike calorimetry, is the longer you look, the less noise you see, and you can actually improve your system by doing that. Okay, so let's now talk about super hyperfine structure. Again, the single line is a hyperfine emission, and when we create sidebands, I'm calling that super hyperfine. So here, this is about 30 kilohertz across, and here the time is going this direction. So here at 2 volts, we've got a very low voltage, we've got a very nice signal, and yet when we up the voltage to 15 volts, all of these other bands appear. So now let's analyze them. This is looking as a function of time. This is at a single moment. And you can see that there's quite a few lines here, and now we're going to analyze them. Oh, and there's one other thing. There's a drift initially, and it stabilizes, and I hope someone here can contact me for the cause of this. We have a lot of hypotheses why it initially drifts, and we'll deal with that later. Tomorrow we'll talk about there are some pulsator lines and what their implication is. So let's talk about the super hyperfine deuterium line emissions. And first, we're going to look for the zirconium oxide components. And we had 2 of them. The first 2 that we looked at, we got these lines from. And we did an analysis for symmetry, for the amplitude of these lines. You know, when you deal with optical systems, the center is always higher, and then it falls off. That's not what we see here. And that's another question I need from you people to tell me why that is. So the symmetry analysis has shown that let me go back a second here. When we take this and turn it around off the central position, there is a 7 to 15% asymmetry. It's quite close, but it's not perfect, and neither are masers. When you look at the Zeeman effect splitting of masers, it's often up to 50%. So this is well within that region. The next thing we're going to look at is resonance broadening. And resonance broadening falls off as 1 over r cubed. And what we are, okay, that'll be next. Looking at the intensity. See, here's the center. I don't understand, this will be the first closest neighbor of where the deuterium is, as I'll show you. I don't know why these are lower frequencies, these are higher frequencies. I am completely clueless as to why the center line is not the largest amplitude, but it isn't. And and here we can see the symmetry, we can see the center, we can see that at lower frequencies we're always getting a higher amplitude than at the center, and I'm completely confused as to why. So please, somebody tell me. Next, let's analyze the position of these lines, because it may tell us something, and that's what we tried to do the following way. Again, the fall off goes as 1 over r cubed, so I did a Gedanken experiment. Let's analyze a face-centered cubic and a body-centered cubic structure, and these things are well known in material science. For example, you can analyze the number of nearest neighbors for distance, for coordination number, how many are nearby at that distance. And what we see, for example, is when we look at the first closest neighbors, there's 12 of them. The distance is the cell structure over 2. Second closest neighbor, there's 8 of them. It's the cell structure over the square root of 2, yada, yada. And we can go ahead with those. And here we have the numbers. Now, initially, when I did my Gedanken experiment, I thought this was a magnetic field interaction. Peter Hagelstein has assured me it's not. So we're stuck with resonance broadening, but it's still 1 over r cubed. And you'll see there's a terrific match. The one we're going to look at was component 7.4, which was driven at 10 volts. And what we have here, here's our plot. This is half the plot. What we do is we take the plot, we look at half. First nearest neighbor is closest. So we're going to get the greatest amount of resonance broadening. That's over here. Also, I took the lowest side and flipped it over here. So we're actually looking at brighter bands that way. So if we look here at the first closest, we see, here's the second closest. This is interesting because a singlet, which we expect, has become a triplet. We'll talk about the implications of that in a second. And here's the third and the fourth closest, and we get a nice match for face-centered cubic. This to this, that to that, this to this, when matching that to that. And over here, we have a very, again, it's a very small distance and frequency. Let's look at the body-centered cubic. It's no match at all. So what this is telling us is in some kind of vacancy, either in the palladium or in the zirconium oxide, which has a rhombic phase, which also has face-centered cubic, there is an active deuterium, which is in a free radical state, which is the penultimate form before helium-4. So we get overlap, we get a match. As I mentioned to you, there's a match of coordination number, a match of distance. Some kind of interaction is occurring at the second closest neighbor. Either there's a substitution of a paramagnetic ion, some kind of magnetic interaction. We're really not sure which, but it does tell us the following. It suggests that the location of the excited state of the deuteron is a face-centered cubic vacancy where this active site occurs. So it's either a Frenkel or Schottky defect within a palladium vacancy, which is slightly modified, as I showed you, for the second closest neighbor, or in the rhombic case of zirconium oxide. And here, for example, is zirconium oxide that shows you one of the forms that it occurs in has a similar state. So we either have a vacancy here or in the equivalent of the palladium. Now, the next one we analyzed was the ordinary water MOAC system, which was built at Lincoln Laboratories. And here's the results. This shows the instantaneous time when it was off, after it was driven for a long time. Here is 10 volts at 45 milliamps, which was the optimal operating point. This is just on the other side of the optimal operating point, and here we have the bands out. So this goes to here, that goes to there. Let's analyze it. By the way, when you look at this, I don't know if you can see it here, but some of the lines are pulsatile, and we'll talk about what that means tomorrow. So here's the center. We can see it's symmetric. We can see that the lower frequencies are brighter than the center for some unknown reason. And here, when we do the correlation, is it face-centered cubic or body-centered cubic? I'm afraid for the nickel, it's rather complicated. Something has changed. It's not what we expect of nickel. And I keep thinking back to what Mike Staker told us at ICCF21, that it is very likely that the active nickel state, when it's activated with deuterons, changes. And here we can see it. And I'm just not smart enough to analyze what's going on. I need you folks to do it. The basic finding is that the results in nickel are very complex and demonstrate a range of face-centered cubic and a few body-centered cubic vacancies, which may herald completely new metallurgical phases in the nickel, unlike the deuterium. So conclusion and findings. 1, higher voltage are needed to elicit the hyperfine sideband structure, which we call superhyperfine lines. Superhyperfine analysis does reveal information of the location, either in palladium or maybe the rhombic zirconium oxide, but it is definitely a face-centered cubic vacancy, which is the active site in one of these. And as I'll show you tomorrow, some of the lines are pulsatile, which may indicate a mass energy change within the lattice, which is requisite in order to get the excess heat. Our symmetry analysis shows that it's actually quite symmetric within 85%, which is much better than some of the Zeeman splittings. And we use resonance broadening, we believe, is the cause of the separation of these superhyperfine lines. Although initially my hypothesis was magnetic field, but I think Peter's probably right. I'm off. We need an answer for why there is a change in the second closest neighbor and what it is. Something happens within the palladium, and that multiplet may be a result of an inclusion of an additional magnetic material or an interaction between the second and fourth closest neighbors. In the MOAC, which is an ordinary water nickel system, we also find the change, but it isn't. Uh-oh. I killed it. Thank you. What we find is that with the nickel, we get something totally unexpected. It's not what we see for normal nickel. There is a change within the nickel requisite. So these are our final take-home points. 1, analysis of the non-Zeeman, because we're not adding a magnetic field, superhyperfine line structure reveals possible insight into exactly where our precursor to helium-4 is occurring. 2, the results indicate, in fact, that free radical deuterium is the ultimate fuel prior to helium-4, and we can clearly see it with this reaction. The fuel generates the fusion product in a face-centered cubic vacancy, either in the palladium itself as palladium deuteride, or a similar vacancy in zirconium oxide, and we're unable to detect which it is. Thank you.
We have time for questions.
Thanks, Mitchell. Have you considered that when you have applied the high voltage, but before avalanche, that you're actually stimulating the Stark effect on that material?
No, that's a good idea.
And also, in the case of the MOAC, when you're using nickel, the nickel is a magnetic material, so it's going to enhance the magnetic field in the material, and you may get a mixture of the Stark effect and the Zeeman effect.
That's a great idea. Thank you. Andre.
I think it's quite interesting that this analysis was done in both palladium and nickel. So would you conclude based on this analysis that if these atomic hydrogen or deuterium spots are the active spots, then it's a similar mechanism of the nuclear process in deuterium and nickel systems?
I do think the deuterons are involved in the nickel system for 2 reasons. At ICCF5, we showed if you dope ordinary water nickel systems, we get more excess heat. with the difficulty being that at some point, as I showed in that paper, the nickel changes structure and then you never get excess heat. The deuterium has a very deleterious effect on the nickel, but both for that reason and the paper that we showed it last at ICCF21, where the deuteron population falls as a result of the excess heat, I do think that in nickel ordinary water systems, we ought to think very possibly that deuteron's the fuel rather than hydrogen. Thank you.